Hey everybody, this is Larry. This is day 27 of the June Leetcode Daily Challenge. Nope, I lied. Day 26 of the June Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's poem. Yeah, not much of an update today. I just ran for 4 miles, I want to say, something like that. I forget. I wasn't paying attention. I was just kind of doing casual, doing it easy, slowly ramping up. I am going to go on the Hansen plan in case anyone's curious. Hansen 18 weeks. Yeah, it's going to be daunting. It's going to be tiring. It's going to be a lot of, I don't know, hopefully not too bad videos. So we will see. I am in New York, so if you're following U.S. politics, it's been kind of nuts, unexpected, but we will see what happens. And also, the only thing that I want to say is, I'm not gonna lie, I'm trying to get out of here a little bit quick. Even though I'm a little bit late, I kind of, yeah, because why? The Bear. Is anyone watching The Bear? Season 4 is out apparently. I didn't even know. I didn't follow until someone was pinging me about it. So let me know in the comments if you're watching The Bear. No spoilers, but yeah, it's something that I've watched for a long time. I guess, you know, since last couple of seasons. All right, anyway, let's get started. Let's take a look at today's problem and let's go. We have 2311, longest binary subsequence less than or equal to k. You give a binary string s and a positive integer k. Return the length of the longest subsequence of s that makes a binary number less than or equal to k. That makes up a binary. Okay, it's it's a binary substring. Okay, so a longest subsequence that make a binary letter or equal to k. Okay, could have leading zeros. Empty strings contain equal to 0. Okay, subsequence can be okay. I know what subsequence is. Though just to be clear, even though I say it starkly, I do appreciate these notes because I don't know. Sometimes I feel like Leetcode prompts are underspecified, where like they tell you something and then they assume you know the definition, and then later you get it wrong and you're like, no, they mean a different thing. Even though they use standard words, they mean a different thing. So I'm a little bit defensive about it. So I appreciate that they have this notes for this problem. In any case, look at an example, right? So k is equal to 5. So we want the longest subsequence of a binary number less than or equal to k. Okay, and k is 10 to the 9 because my first thought may be that if k is small enough, we can try. I don't know if it's brute force necessarily, but like a greedy approach where you go, okay, well, let's try. What's the longest subsequence of number where k is 0, k is 1, 2, 3, 4, all the way up to the exact actual k, right? And then because you're looking for a specific number, it'll be easy to find the longest subsequence of that number, right? And yeah. And for this one, yeah, I don't know off my head though. Given that k is this number, yeah, and n is 1,000. Does that give me anything? I don't know. I mean, I think the first intuition is that k is at least 1. Okay. I mean, for example, you can have the entire, like, I'm trying to think, like you know, a lot of these problems we're trying to make decisions at every branch, right? Like maybe some idea, maybe like a take no take for each index or each integer, right? Also, my apologies if I'm like going a little bit slow or confused because right now I do not know how to solve it, to be clear. So I'm talking through my thought process, and after all, that is the point of these channels. It's not necessarily an explanation channel, even though that could be good too. But there are also a lot of explanation channels, right? For me, the more valuable thing is that I want to show you someone who maybe is good. I don't know. You could think whether I'm good or not, but at least someone going through that thought process of someone who so that's what I'm thinking, right? I think my first thing is just thinking like in a greedy way, or not necessarily like the longest subsequence, but if you have all zeros, that's a very good long one, right? Or in this case, it's all zeros and an extra one at the end. So that would give me a long-ish subsequence. And I think from that, I almost want to think about something like this backwards, if that makes sense. Because then now, because then now, I think if we go from right to left instead of left to right, because if you go left to right and you take a digit, then you have to shift and add. And I think in that shift and add, there's a lot of, well, not that there's a lot of uncertainty, but it just, there's a lot to factor in, right? Because for example, if you have this number, let's just say from the example, right? If we want to say take the zeros and then because it's 3, and then now we're at this 1, and we have to go with we want this 1. All right, let's just say for a purpose we want this 1. But then now if we add the zeros, that means that, you know, now we're dealing with a number that keeps on multiplying. So these zeros have a lot of impact on choice, right? But if we go from right to left, let's say we have this 1. Okay, well, our current number is 0. So if we take this 1 and then we keep taking zeros to the left, well, what happens? Well, it still doesn't change the number, right? This number is still 1, which is still under k. So this, I don't know if that makes sense, but I think from that, there is some sort of an invariant of a feeling there, right? I'm not, still again, right now, I don't have a proof or even an inkling of whether that's right, but that's an idea that I'm playing around with, right? Because here, you could almost even say now, at this point, you could even say now, at this point, you go in a greedy way. Let's say we have this 1, right? We can even fake take it, maybe, right? In the sense that if we take this 1 and we can even do the math for, let's just say it is done. This is the last number that we take by putting all the other zeros, right? And from that, it doesn't change the answer. It doesn't change the property of this, the value of this number, but it gives you a longer subsequence, right? So you could kind of do like, okay, well, this is 1. But then how do you build it incrementally? So that you have this 1, you have some zeros, so you process the zeros, and then now you have this 1, right? Then what happens? Well, I don't know. Honestly, I'm not sure that I'm going the right way about this. This feels very weird. But here, at the very least, I can think about, okay, well, we add this, at least we know the true cost of this, which is going to be, well, this is in a 1 digit, 2, 4, 8. So that means that this number is now a 9. And then we figure out from k whether we want this to be a 9, or we start from here instead. And maybe kind of construct a DP based off that or something, maybe. I don't know. It's a very awkward problem. Am I missing some weird thing? Subsequence part is a little bit awkward because then now here, let's just say we take this and the k is 9 or something, so that this is smaller or equal to it. Then now we could take the 3 zeros to the left, right? My thing about this choice thing though is that, okay, for this one maybe that's fine, but what if we have a smaller k and then we just do this instead? Like, how do we choose between this and maybe not taking the 0? And then maybe taking a 1 later on. Would you ever want to do that? I think that's the part of greedy that I'm trying to figure out. And maybe you would, right? No, I think there's an exchange principle here, actually, now that I think about it, right? Because the question about making a decision, which this is one of those problems of like making a decision of either take, no take, going from right to left. The thing that I'm thinking of is that, okay, like we're going from right to left on this thing. We took the 1 all the way on the right. We take some zeros maybe, right? And maybe if adding this 1 is too big, then we shrink by removing some previous zeros. But then the question is, okay, right? or even if we don't need to, do we ever, or the question is, do we always keep this 1? And I want to say, and I'm not sure about this, but I want to say the answer is yes, because if we want to add 1 later on, well, there are 2 things. Like, the only reason why we don't want to keep this 1 is, in a way, if we don't have this 1, then maybe later on there's a 1 that will help us give a longer answer. But the question is that possible, right? And I want to say the answer is no. And the reason why I say this is because that now, from this 1, let's say this is now max, like there's no, in a lot of these decision problems, the thing about swapping a later 1 is that, or like making a decisions, or in a non-greedy kind of, or a counter example to a greedy would be that you exchange the 1 that you have here for this later 1, but open up possibilities of more 1s in the future or something like that, right? But the question is, but I don't think that's possible, because here the smaller 1 is strictly better than this 1 because of, I don't know if it's exchange, but it's just like this idea that, okay, well, for example, you can always, if nothing else, this earlier 1 that we saw is strictly better than this 1, right? Because anything that, I'm probably not describing this quite well, but in the sense that there's a replacement or an exchange idea that this 1, like at best, this 1 will have 2 zeros after it, right? Like if we remove this 1, then yeah, at best there are more zeros, but in that case, then that is the same as just like having this 1 like this, right? So I want to say that in that sense, maybe greedy is able to do it, and then check. And then my later question is that, okay, let's say we have this, right? So, okay, so let's say in this case, I'm just going through a lot of cases and maybe not in a straightforward way, but let's say k is, I don't know, 5, right? Then now we try to add this is too big for k, so then we subtract one of the zeros. Do we, oh, actually, do we want to subtract? I was going to say, if this is too big, then we subtract one of the zeros. But actually, we could even do better, right? We could actually just subtract one of the 1s, because just for any string, let's say you have this string, then now you could either subtract one of the previous 1s, so then you get this, or one of the previous zeros, we get this, and this is a strictly smaller number, so it is strictly better, right? Does that make sense? Hopefully that makes sense. I think I'm trying to make sense of it, so I'm not like in a convincing, I'm convincing myself even, right? That's why like greedy problems are very hard for me, because you have to do all these, for me, like a lot of exhaustive proof, and I don't know that I see anything dynamic programming, though I could very well be wrong. We could walk through an example, right, and then kind of see what I want to do. So let's say you have this one, which is example 1. Okay, so we go right to left, right? So we have 0, okay, and then here we just do a quick check because we know how many zeros are in here, right? We could do easy pre-processing. So there's 3 other zeros, not including this one, which would give you a 4-digit best answer. So we just kind of store it in the best. And then now you have a 1, right? Okay, so now if you add the 1, what happens? Well, it's going to be smaller than 5 because this is just 2, right? And then we add the 3 zeros to the right, so then now the best answer is 5. Or, well, this answer is 5 and the best answer is 5, right? And then now you have 0, 1, 0, which again, we don't have to do anything about, or that's the answer that we already had, so it doesn't change anything. So the answer is still 5. And then now we have 1, 0, 1, 0, right? Well, 1, 0, 1, 0 is bigger than 5, so what is that? That's 10, right? In binary. So then now we have to remove a digit to kind of almost like shrink it so that we, get the answer. And here, that's what I was saying, is that you could remove a 0 maybe, sure. But actually you go just remove a 1 because in a greedy kind of way, this will always give you a better answer because you're removing a digit. So then that means that now, what happens when you remove a 1? Maybe I'll put it here. and maybe I'll write it this way. This for not counting, and then on the left there are 2 more zeros plus 3 digits, so this is also 5, right? And then the next digit we have, it doesn't change anything because it's a 0, so we already kind of did the math. And then here we have also doesn't change anything, right? And then now we try adding this 1. So we have this, which is clearly way bigger than 5. Wait, is this 5? Oh yeah, this is 4. Right, this is way better than or bigger than 5. So then we remove a digit. We remove 1 digit. Huh. I mean, yes. But also no, right? Am I doing this right? This is so confusing. I mean, yes, and then now maybe you want to keep on shrinking, but that's not. But that, I mean, sure, that'll give you an answer, and this is like 3. But that's not even the best way about it, right? Because the best way about this is actually given. That's why I'm pausing. If we had something like this, the best way about it is actually just removing the leading 1, right? Like we're gonna remove 1 digit, we just remove the existing 1, and then now we're good. Now we're 5 digit again. So that means that because if we're forced to remove a digit anyway, because the number is too big, then we just remove the existing number. So actually, like, and that's why I pause is because now I'm going back, and here when we insert this 1, let's go back a second, right? So I was wrong here. I mean, it turned out to have the right answer, but let's say we have something like this. Well, again, we can remove this 1, but we can actually also just remove this 1, right? Because now instead of 4, the answer is 2, and and then now you add it to the other 2 digits with 3 digits, so this is also 5, and then dot all the way. Because if you kind of compare this with the rest of this that we drew out, replacing this with a 1 and this with a just removal, this number is smaller than all of these, so it gives the same answer or better. Greedy is hard, but I think I get it now, right? So I think hopefully that makes sense, and I think that's what I'm trying to do. Okay, so then let's just practice this one for a second. For example 2, let's walk it together. People say that I don't walk things together enough, so well, there you go. But yeah, so then now k is equal to 1, so we start with 1. The answer is going to be, well, this 1 digit plus the number of zeros in the prefix, so that's 5, so that's total 6, right? And then now we have 0, 1, that's still good enough. I mean, of course, it's just going to be 6, so 0, 0, 1, also 6, right? No change. And then now you have 1, 0, 0, 1, and again, that means that this number is too big, and we have to remove a digit. And like I said, maybe you can remove this and then this and then this to use this 1, but what if you just don't have to? What if you just skip it, right? Because it's subsequence, so you have 6, and then now that's it, right? We dot it out. You have this 1 and you skip. Man, I have to watch my video from last time. Why? I feel like today I really struggle with this one, but maybe I just missed the logic. I mean, I think going backward was a great move, but then after that, I just kind of, just like wasn't confident about this at all. Maybe it's the heat. I blame it on the heat, right? Okay, so then now we can say best is equal to 0 for the longest. We actually also want to write s.count of 0, right? So zeros is equal to this, say, or maybe z's for zeros, right? So you have best, you have z's, and then now you have the current thing. So the current is just the accumulation that we talked about. So then now going to the last digit, we have x is equal to s sub I. Let's convert it to an int. If x is equal to 0, then we have to subtract this away. Yeah. Oh, sorry, whoops. I said subtract and but we also want to count the current. So current is actually the number, but not the number of digits. So actually, maybe I need 2 things. Current being current is against k, is what I meant. The current number against k. So the subsequence value. Right? Okay, and then now we have 0. If it is a 0, then also current number of digits just went up, right? Because it's a freebie. Because we always add it to the prefix, so then it's a freebie, right? Else, else we have a 1. Oh, we have to update this anyway, so maybe we don't. I mean, we do, but maybe we don't have to do it yet, right? Well, current digits is just gonna be best as you go to max best current digits, right? I think that's fine. And because it doesn't, we don't change current because we just add a 0 to the front. And then now here we want to add a, oh no. I mean, this is right-ish. I mean, I want to say we can, the way that I did it is that I would have added ZS, assuming that we want to add the prefix. But now examining or re-examining the algorithm that we have, we are going to go through all the zeros and they are going to be added in the future anyway. So I don't even think we need to keep track of the Z's or the zeros anymore. Even though we can, if you want to, I think maybe that's more for real, but we don't even have to because, yeah. And then now you have a 1, then we want to check whether we want to add a 1 to the beginning, which is going to be, so yeah, it depends on the number of current digits. If the current number of digits is 1, what happens? If it, sorry, give me a second. If the current number of digits is say 1, then now we want to add a 1 in the second digit, so it's going to be 2 to the power of current digits, right? And you could do shift. I know that I could do shift. I just want to kind of be illustrative a little bit. So then we can do something like this. So then with this plus this is less than or equal to k, then now we want to add the current number of digits. Current we added by this power thing. And then again, we can just update best here. And that's it, I think. Give it a quick submit. Hopefully, no silly mistakes. Huh. Well, I mean, did I miss something? If it's because we want to remove it, because this is greedy, so I'm trying to think in what case is the greedy wrong. Well, we have this case, but do we need to keep track of the zeros thing? Because we always add it on later anyway, so it's never a thing anymore. Then why am I wrong here? X is 0, 0, then x is equal to 1. Oh, I'm dumb. I order of operation. Dummy. I just wrote it very sloppily. Because I mean I checked this and then I incremented it before adding it. Okay, very silly mistake. But yeah, hopefully this was good. Yeah. I was gonna say like, yeah. I mean, hopefully, well, one is I still hope that this is a good enough video for you to kind of go through a greedy problem, right? As you can see, I struggle with this one a little bit, or at least with the proof. I think also, honestly, just to full disclosure, is that if this was a contest / I'm trying to get it out as fast as possible versus trying to explain it, I probably would have YOLO'd a lot earlier. That said, because I'm trying to. Because for me, the burden or the threshold for YOLO submit is much lower than the proof that I'm trying to bring to you, even if it's not too high, right? And I think there are a couple more observations here, right? One is that given this is 10 to the 9, that means that if we have the TLDR is that if this gets too big, even if k is 10 to the 9, the answer is at most. Well, actually, that's not true. It's not that the answer is at most 30, but you just skip ones at a certain point after that, right? Like you just stop adding ones because anytime you add a 1, then it will be too big. Because in this case, the way that I wrote it, it does not work in all languages, right? Because in say Python, well this is Python, But in C++, this would overflow. Current digits could be 1,000, say, right? You got 1, 1,000. For example, you could have something like 1 and then a lot of zeros, right? And I don't know, and it just would end up, this is a very expensive function as a result, because I mean I didn't put enough zeros, but you get the idea. If this is 1,000, then it's gonna be power of 2 to the 1,000, which is a lot, and stuff like that, right? And maybe you put maybe all ones is actually worse in terms of performance, and it kind of shows up here, right? Oops. Oh, faster than last time somehow, but yeah. So what I would do, and I'll optimize it for another language, because I just want to point out that this is not strictly correct in all languages. But let's say you want to keep it in 64 floats, right? Then here, maybe I would say like, if current digits is, I don't know, greater than or equal to, even just 40, we just skip, because this will never be true is what we're saying. Otherwise, then we do this, right? So this would make it a little bit faster, I think. Give a quick submit. It may not come out. Okay, I mean, as you can see, it is faster. Sometimes it may not come out because when you're dealing with milliseconds, it's a rounding error depending on how Leetcode handles it. But yeah, and if you use another language, just having this if statement should be good enough, assuming you use a 64-bit int, right? And you just need a number that's bigger than 30 or 31 maybe, and that's it. Am I good? So what's the complexity here, right? I mean, it's just O of n, so I think we're okay. I mean, you could say that maybe this makes it n squared if you're not careful, but even then, I think having this bounded would give it just at most, because then now this thing is at most 32 shifts, if you will, even though technically yours it's a mod power, so it's actually smaller than that. So it's like a log n, or not log n, but log k, if you want to call it that, right? So it's gonna be, which is effectively constant for real values. So it's gonna be n log k if you want to call or power as a function. But yeah, that's what I have. But this is linear-ish, so I think that's why I was giving a pause for like, why is it 1,000? Because I think you could do this in linear, right? Which, well, we did it in linear. But yeah, I want to take a second to see what I did last time, which is about, jeebus, 3 years ago almost exactly. And what did I do? Oh, I guess oh, we count the number of zeros and then we just add one greedily. Oh, I reversed. I was like, how does this work? I reversed it earlier. I see. I missed that. No, I mean, so this is basically the same. I mean, I know that I did the power thing, but yeah, and in this, I mean, I kind of didn't do it this way necessarily, because I did the zeros thing, but this is basically how you do the zeros thing. I gotta watch that video. I'm curious about the former Larry's logic, because this is way more beautiful than what I have today. And today I took a while, as you saw. It took like, I think this video is about 28 minutes long right now. So yeah. Anyway, yeah, let's call it a day. Thanks for watching. Yeah, that's it. Thanks for watching. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.